So students, after covering the chapter number 4, that is the magnetic effect of current, our next chapter, that is chapter 5 of syllabus, is magnetism. In this chapter, we are going to discuss about the properties of magnet, the magnetic effect, about the artificial or the natural magnets. And these are the topics we are going to cover, the topics in this chapter, like the bar magnet, its properties, solenoid case, then the bar magnet and its dipole moment, Coulomb's law in magnetism, and so many other topics. So the first topic of this chapter is magnetism. What magnetism is, or what is a magnet? Basically, a magnet is a material that has both attractive and directive properties. It attracts small piece of iron, nickel, cobalt, etc. And this property of attraction is basically called the magnetism. So a body possessing the property of magnetism is called a magnet. And a body possessing the property, basically the phenomenon of attracting magnetic substance, or we can say that a magnetic pole is a point near the end of the magnet, and the magnetism is concentrated at that particular point. So before discussing the properties, let us discuss about the field or periphery of a magnet. So the region around a magnet in which it exerts force on the other magnet and on objects made up of iron, cobalt or nickel is called the magnetic field. And earth is basically a natural magnet we are having. So the pole is a point near the end, and we are having the strong magnetic field at that particular pole region. And as we are moving away from that pole towards the center or away outside the magnet, in that case the magnetic field of that particular magnet goes on decreasing and decreasing. Now there are so many types of magnets we are having, like the bar magnet, the magnetic needle, horseshoe magnet, or the ball ended magnet. And all these magnets show some basic properties. So the properties of magnets are: number one is the directive property. When a bar magnet is suspended freely, it aligns itself along the north and south direction. So this is known as the directive property, that is related to the direction along which the magnet is being aligned. The next one is the attractive property, that is unlike pole attract and the like pole repel each other. So this is the common property. You are aware that like repel and unlike attracts. After this, we are having that magnetic poles always exist in pair. A magnet, if we are cutting, crushing, breaking a magnet, each and every piece of that broken magnet or the granule of that powder magnet is having two poles. One is north pole, another one is south pole. So a magnet always exists in dipole. Next property is a magnet can induce magnetism in another magnetic substance. So whenever some magnetic substance like iron, nickel or cobalt is placed inside or near a magnet, in that case they attain or gain the magnetic properties. And you must have seen that all pin box in which a strong magnet is placed and the pins are aligned to that magnet. So whenever the pins are taken out, in that case they are showing or behaving as small or weak magnets for a bit of time. So this shows that the magnetism is induced, and this property is known as the magnetic induction. And again, we know that a magnet always attracts the magnetic substances around it, like the iron filling, like other magnetic substance. So these are the basic properties of a magnet. Now the most important thing about magnet is that repulsion is the surest test of the magnetization. So when a magnet, and we know that a magnet can attract another magnet, and also it can attract the magnetic substances like iron, nickel, cobalt, etc. So how to differentiate that a magnet is attracting a magnet or some magnetic material? But we know that a magnet can repel another magnet only, and it will not repel any magnetic material. So repulsion is the surest test for the magnetization. After that, let us discuss about the representation of the magnetic field. So we are having that these lines represents the uniform magnetic field. So a magnetic field in a region is said to be uniform. We know that if it has same magnitude and same direction at all the points of that region. And a uniform magnetic field always acts in the plane of paper, and it is represented by equidistant parallel line as shown in this figure. So this uniform magnetic field acting perpendicular to the paper and directing outwards, that is represented by the dotted line, and if it is represented by the cross, in that case the magnetic field is inward. So this is the case, we are having uniform magnetic field on the plane of paper or diagram. These cross represents the magnetic field, uniform magnetic field perpendicular and into the plane of paper, and these dotted line dots represents the uniform magnetic field perpendicular again and emerging out of the plane of the paper or the diagram. So we know that magnetic field is space around a magnet, and we are having three different cases. One is on the plane, another one is perpendicular inward, and the third one is perpendicular outward. Now some more definitions are related to this magnet, like what are magnetic poles, what is magnetic axis, equator and length. We are going to discuss those things. Let us first discuss about the current loop as a magnetic dipole or its dipole moment. We know that a current carrying loop behaves as a magnet. So one face is behaving as north, another one is opposite face is behaving as the south pole. So for that, let us consider that we are having a current carrying circular loop and current I is flowing through that loop, and this dot represents the direction of the magnetic field which is emerging out, and here it is representing with the arrow that B is the uniform magnetic field emerging out through this center of this circular current carrying loop whose area is A. Now from which face the magnetic field is coming out over here, that is representing the south pole, and here this represents the north, and here this is the plane of this current carrying loop. Now the main thing to remember over here, while we are figuring out which face represents the north, which face represents the south, when we look at any one side of the loop carrying current, if the current is anti-clockwise direction, then the side of the loop behaves like magnetic north pole, and if the current is in clockwise direction, then the direction and that side behaves as the magnetic south pole. So you can see from this figure that for this phase the current is anti-clockwise, so this phase behaves as north pole, and for this we are having the clockwise, and this phase behaves as the south pole for a given magnet. After that, like the electric dipole moment, we are having the magnetic dipole moment as well, and the magnetic dipole moment is given by m is equals to IA into the unit vector, where I represents the current flowing through the solenoid or the loop, and A is the area of cross section, and N is the unit vector representing the direction. And the SI unit for this magnetic dipole moment is ampere meter square. Now, let us discuss the case for a solenoid. How the solenoid is behaving as a bar magnet. So we are having a current carrying solenoid, and this is, you can see from this figure that we are having a solenoid, and in this case the current is flowing through this solenoid, coiling of this solenoid, and these are the magnetic field lines at each and every particular point on that solenoid, and this as a whole is representing the total. And this face, you can see that the current is entering, so this face is representing the south pole, and here the current is in this manner, so it is anti-clockwise, so this face represents as the north pole. Similarly, you can see from this figure that the current is flowing in this clockwise direction, so this will become the south here, and here the current is anti-clockwise, so this will become the north for this particular region over here. Now this you can see from this face that here for this upper we are having this as the case of a magnet. We are having one end as the north pole, another end is behaving as a south pole. So this current carrying solenoid is also behaving as a bar magnet. So we are generally in a habit of using that current carrying solenoid is actually a bar magnet, and we are using the application of this solenoid in order, or like in electromagnetism, in order to produce the strong electromagnets for our purpose in like industries and all. Now, after discussing this case of solenoid, let us discuss about the bar magnet, some terms related to the bar magnet. Like in this case we are having a bar magnet, and this is a point P at the north pole, and again we are considering a point at the south pole. So these 2 points are the points where the magnetic field is strong for this particular bar magnet, and this represents the direction of that magnetic dipole moment. And here this is the magnetic length between the 2 points where the field is very strong. So this length between P and P is the magnetic length for a given magnet, and the whole length of a magnet is known as the geographic length for a given magnet. Now, let us define what is known as the magnetic axis. So basically, the line joining the pole of magnet is called the magnetic axis. That is, the line passing through the pole of magnet is known as the magnetic axis of the magnet. After that, we are having that the distance between the pole of magnet is called its magnetic length. We had already discussed. And what is geographic length? That is the original length of a given magnet. And after that, we are having another term that is known as the magnetic equator. The line passing through the center of magnet and at right angle to the magnetic field. So this is, suppose the line is passing through the center and perpendicular to the magnetic field here. This represents the magnetic equator for a given magnet. So this is magnetic length, this is geographic length, this is your magnetic dipole moment, and the line passing through here is known as the magnetic equator, and the line passing through the axis, this axis of this magnet, is known as the magnetic axis. Now, the ratio of magnetic length and geographical or geometrical length is nearly equals to 0.84. So the magnetic length is always a bit less than the geographic or geometric length of a given magnet. Now let us discuss the terms or define the terms magnetic dipole and the magnetic dipole moment for a given bar magnet. A pair of basically magnetic poles of equal and opposite strength separated by a finite distance is called a magnetic dipole. So we are having 2 poles. One is north pole, another one is south pole. And this as a whole is known as magnetic dipole. And if we multiply this dipole with the length of that magnet, we are getting the magnetic dipole moment. So the magnitude of dipole moment is the product of pole strength M and the separation between the 2 poles, that is 2L, from the center of the magnet. and the SI unit of pole strength is ampere meter. So the dipole moment is m vector is equals to m into 2L. This small m represents the magnetic strength, pole strength, 2L represents the length of the magnet, and this I represents the flow of current through that particular magnet. And the SI unit of pole strength is ampere meter. Now, after discussing these basic definitions for the bar magnet, let us now discuss about some laws related to those magnets, as we had already discussed in our previous chapter, number 1, Coulomb's law in electrostatics. Similarly, we are having Coulomb's law in magnetism as well. So what is that Coulomb's law in magnetism? The force of attraction and repulsion between the two magnets, that is, the pole of magnet, is directly proportional to the product of their pole strength and inversely proportional to the square of the distance between them. Now, let us consider the case we are having two magnets. One, we are considering the pole number 1, that is pole strength is m1, and for another magnet the pole strength is m2, and let R is the separation between these two magnets. Now, according to Coulomb's law of magnetism, the force between these two magnets, either that is repulsive or attractive, in that case the force is proportional to the product of pole strength, that is m1 and m2, and it is inversely proportional to the square of the distance between the two magnets. Combining these, and we are getting that F is equals to K, that is a constant of proportionality, K m1 m2 upon r square, or we can write it as that F is equals to mu naught upon 4 pi m1 m2 upon r square, where K, that is equals to mu naught upon 4 pi, is a constant, and here mu naught value is 4 pi into 10 raised to power minus 7 Tesla meter per ampere. And in vector form, we can write this Coulomb's law in magnetism as F vector is equals to mu naught upon 4 pi m1 m2 upon r square into r unit vector. This r unit vector basically represents the direction of force, and we know that r unit vector can also be written as the vector r divided by the mode of this r, and again we can write as the net resultant force of attraction or repulsion between two bar magnets in vector form is written as F is equals to mu naught upon 4 pi m1 m2 r vector divided by r cube. Now, after discussing this Coulomb's law in magnetism, we are having some other topics, like we can find out the magnetic field of a bar magnet at an axial line and the magnetic field of a bar magnet at an equatorial line, and you are now familiar with these topics as you had already covered these topics in previous 2 chapters. So we are going to discuss these topics in our tutorials or the classes as well. Now, after discussing the Coulomb's law in magnetism, let us discuss some important definitions and terms related to that magnet, that is related to the Earth's magnet, or how the Earth is behaving as a magnet, or the magnetic strength, or the magnetization. So many other definitions we are having. So we are having the first thing is what is magnetic intensity, or what is the magnetizing force. So a magnetic intensity at a point is the force experienced by the north pole of unit pole strength placed at that particular point due to the pole strength of a given magnet. And the symbol for magnetic intensity is H, and this H is equals to the magnetic field divided by mu. So this is the magnetic intensity, and it is also defined as the magnetomotive force per unit length. So many other terms are related to this magnetic intensity. The SI unit is ampere turns per linear meter, and it can also be defined as the force experienced by a unit positive charge flowing with unit velocity in a direction normal to the magnetic field. And its SI unit is ampere turn per meter or ampere meter, but its CGS unit is known as Oersted. Now the name is familiar. What do you understand by this Oersted? Oersted is basically the name of the person who explained the magnetic effect of the flow of charged particles or magnetic effect of current. Now after this magnetic intensity, our next heading or the topic is the magnetic field strength or the magnetic field or magnetic induction or magnetic flux density. Any name you can give that. So what is this magnetic field strength? Basically a magnetic flux density, as you know that the flux are number of field lines crossing a unit area. So magnetic flux density is the number of magnetic field lines of force passing normally through a unit area of the substance, and it is represented by B is equals to mu naught H. So this is our magnetic flux density. After that, the SI unit for this is Weber per meter square or Tesla, and its CGS unit is also known as, that is Gauss, and 1 Gauss is equals to 10 raised to power minus 4 Tesla. So this is our magnetic field strength or magnetic flux density. After this is our magnetic flux. Now what is this magnetic flux? It is defined as the total number of magnetic field lines of force passing normally through a surface, and its SI unit is Weber. Now there is a relation between this B and H, that is magnetic field, and our term that is magnetic induction or magnetization. So that is B is equals to mu naught H, where mu is the permeability of the medium. Now another definition we are having is magnetic permeability, that is mu. Permeability means we are permitting something. So it is the degree or extent to which the magnetic lines of force can pass through or enter a substance. And here the SI unit is Tesla meter per ampere or Weber per ampere per meter. And relative, next is relative magnetic permeability, that is mu r. Now this is the ratio, as the word relative is connected over here. So this is the ratio between the permeability for free space and the permeability to the medium. So here it is a ratio of magnetic flux density in a material to that in vacuum. And it can also be defined as the ratio of absolute permeability of the material to that in vacuum, that is mu r is equals to B by B naught, or mu r is equals to mu upon mu naught. Now our next term is the intensity of magnetization. Now what is this intensity of magnetization? When a magnetic material is placed in a magnetic field, it gets magnetized, and the magnetic moment developed per unit volume of a material when placed in a magnetic field is called intensity of magnetization, or simply the magnetization. So here it is magnetic dipole moment per unit volume, and we are having the formula that this is equals to I is equals to m upon V, and if we are multiplying it, dividing it by 2L, so in denominator we are having this 2L cancel out, we are removing that. This m represents the magnetic dipole moment, so that is equals to m into 2L, and here it is volume, that is equals to area into the length. So we are separating this 2L in denominator and numerator, and we are getting this intensity of magnetization as is equals to m upon a. That is the pole strength divided by the area of that particular magnet. The SI unit of intensity of magnetization is ampere per meter. Here, now the next term we are going to discuss is the magnetic susceptibility, and basically this is the property of a substance which shows that how easily a magnet can be magnetized. So this represents the property, and it can also be defined as the ratio of intensity of magnetization in a substance to the magnetic intensity H applied to that substance. So here susceptibility for magnetization is I upon H, and as this is the ratio of two similar we can say the quantities, so this susceptibility is not having any unit. This is a ratio. Now there is a relation between this magnetic permeability, that is relative magnetic permeability mu r, and the magnetic susceptibility psi m, and that relation is mu r is equals to 1 plus psi m, or that the relative magnetic permeability is equals to 1 plus the magnetic susceptibility. So far we had discussed the terms related to a bar magnet, the strength and other properties we had discussed about that magnet. Now we are going to discuss about the magnetic field due to a bar magnet on the equatorial line. So in the case of Coulomb's law, we discuss about the magnetic field due to a bar magnet at the axial line, and here we are having the special cases for that, and we are having in this case that we are having a bar magnet, of course that is known as the magnetic dipole, and we are first discussing the magnetic field due to a bar magnet at a point on the axial line of that bar magnet. So here we are having a bar magnet. These two dotted points represents the pole strength or the pole of a given bar magnet, that is the north pole and the south pole, and here this m represents the magnetic dipole moment for this particular bar magnet, and here this is the length from the center of the bar magnet to the south pole, and this represents the length L again from the center to the north pole, and this total length of this given bar magnet will be L plus N, and that is twice of L. This is the line we are considering along the axis of the magnet, and we are considering at any point on this axial line, and for this the distance of this point from the center of bar magnet is x, and this Bn represents the magnetic field due to this north pole that is away from the magnet, and here this Bs represents the magnetic field at point P due to the south pole that is towards the magnet, and here we are having the magnetic field at P that is equals to Bn minus Bs, and we had discussed and derived so many derivations for this in our electrostatics, current, electricity, potential as well. Now the magnetic field at P point is, after the derivation, comes out to be mu naught upon 4 pi 2 mx divided by x square minus L square whole square. Now if this L is much less as compared to the x, in that case we can have the net magnetic field at point P on the axial line will be mu naught upon 4 pi twice of magnetic dipole moment divided by x cube. And similarly we can find out the magnetic field at a point on the equatorial line of a bar magnet. Now let us consider the case. We are having a line passing through the center of this bar magnet, and we are considering at any point Q where we want to find out the magnetic field due to this bar magnet. Now these two, Qs and Qn, represents the distance of this point from the poles, and here it is making an angle theta with the plane of or axis of this bar magnet. This Bn represents the magnetic field at point Q due to this north pole that is directing away from this point, and here Bs represents the magnetic field at point Q or experienced by point Q due to this south pole, and it is directed towards the magnet. Now this can be resolved into two rectangular components. One is perpendicular and another one is horizontal. So they are oblique and they are making angle theta as we are considering the symmetry. So this BQ is the net magnetic field at point Q due to this BN and BS, and these both are having angle theta. And again we are considering that horizontal component, and again neglecting or ignoring the perpendicular components. They get cancelled out in both the cases for Bn and Bs. So the net magnetic field at point Q on the equatorial line for a given bar magnet is BQ is equals to mu naught upon 4 pi m upon y square plus L square 3 by 2. And again, if this L is much less than this y, in that case the net magnetic field at any point on the equatorial line for a given bar magnet comes out to be BP or BQ is nearly equals to mu naught upon 4 pi m upon y cube. So the magnetic field at a point on the axial line acts along the dipole moment vector, and the magnetic field at a point on the equatorial line acts opposite to the dipole moment vector. And these are the cases we had already discussed for the axial and the equatorial lines